So we are introducing the sequent calculus. And first, let me do a natural deduction, a recap of natural deduction, which is what we talked about. So the main idea is that internet is not coming there. I'll try from here.
Jam, we can't hear you. We can't hear you.
What about now? Can you hear me?
Yes, now I can.
And the screen is okay?
Yes, sir.
Yes. Okay. So, yeah.
Again, not able to
We are
hear,
not
sir.
again. So maybe you could turn off your video.
You're not audible, sir.
So you're not audible.
Okay. What about now?
Yes, sir.
And is the screen moving or is it stuck?
Yeah. It's moving.
Okay. Yeah. So this is what I said is the spirit of natural deduction proofs, and there's only one axiom: alpha implies alpha. And for every construct, we have exactly two rules. One is an introduction rule, and the other is an elimination rule. For implication introduction is exactly what I just said. You make an assumption alpha, and from that, you go on to prove beta. Then you can derive alpha implies beta, where you discharge the assumption alpha. Note that it's very important to nest assumptions. So, for instance, suppose there are two assumptions. There is alpha, an assumption, and then there is a beta, and then there is a gamma. You can't write alpha implies gamma. It's beta implies gamma, where you discharge beta, and then you can discharge alpha by writing alpha implies beta implies gamma. Now, so nesting is important, scope is important, so you have to be careful about all these things. Implication elimination is exactly modus ponens. Then conjunction, this is the natural rules that you think of. If you have derived alpha, if you have derived beta, you can derive alpha and beta. On the other hand, conjunction elimination is if you have derived alpha and beta, you can derive alpha or beta, whichever each of them. Disjunction, introduction is straightforward. If you have derived alpha, you can weaken it to alpha or beta. What about elimination? This is what we discussed at length last time. Is that if you have derived, this is case analysis. If you have derived alpha or beta, and assuming alpha, I can derive delta. Assuming beta, I can derive delta. In all the cases, I have derived delta. Therefore, I can say delta. So, and this is a very important difference thing. So, in natural deduction, disjunction is about case analysis. So, in particular, very often you will make the assumption, well, either this is true or it is false, right? Alpha or null. Assuming alpha, I derive delta. Assuming not alpha, I derive delta. In both cases, delta holds, therefore, right? This is the way we actually do case analysis. And this is again the way mathematicians tend to write. For negation, as I said, I introduced this rule. And but if you see the literature, there are different forms of negation introduction. Rightfully, this should be called, false introduction and false elimination. From a contradiction, you derive false, and assuming negation alpha, if you have derived false from that. But as I said, there are different versions of treating negation. So today I'm going to. So this is one proof system, and like I said, you can prove that natural deduction is complete by showing that all the rules of natural deduction are actually derivable in the Hilbert system. That's something very straightforward. You try it out, and once you have them derived in the Hilbert system, therefore it means that whenever a formula is valid, we already know that there is a proof in the Hilbert system. And now we can derive the natural deduction system. Yeah. So you can all basically this completes. And now to sequent calculus. This is both natural deduction and sequent calculus were defined by Gerhard Gentzen. Gerhard Gentzen was born in 1905, died in 1945. Made major contributions to the foundations of mathematics and especially the natural deduction of sequent calculus. He died in 1945, immediately after the Second World War, and he was arrested in Prague and deprived of food. So he was all of 36 years old, and he wrote landmark papers in 34 and 35. Those years, 1931 was Gödel's paper, 34 and 35 were Benzon's papers, 36 was Turing's. These were the years where mathematical logic leaps and bounds. So if Gödel's paper in 1931 founded, I call it the beginning of mathematical logic, and Benzon's paper was the beginning of So they were both introduced by Gentzen in 1934, and his main interest was in proving the consistency of arithmetic. Now Hilbert had proved the consistency of geometry, and in fact that was his PhD thesis, and that was where he actually showed that Riemannian geometry was actually consistent. And this was very important because after the Euclid's parallel postulate, it was clear that these were independent. There was non-Euclidean geometry around, but how do you show that these were consistent? And Hilbert did this, and along with Bernays, wrote this Foundations of Geometry. Question was arithmetic. How do you prove the consistency of it? And this was a major project, and Gentzen wanted to take it up. He tried with natural deduction, and his whole idea of formalization of natural deduction was this is how mathematicians do proofs. But he couldn't do it, and therefore he introduced the sequent calculus and used it to prove the consistency of arithmetic. And his proof of consistency of arithmetic and that ordinal epsilon naught is one of the most beautiful landmark results of mathematical logic. We won't be able to do that proof here, but I hope I'll at least do some bit of consistency of the system that at least we can talk about. But even that will take a bit. I would say it's become the most cherished tool of proof theory. And you will see why. It's really beautiful. So, for Gentzen, each step in a proof is a judgment. When you write down a statement, you are making a judgment. And so, for him, this idea that from passage from assumptions to conclusions is not like in the Hilbert case, the entire proof or existence of a proof, but every step is actually passage from assumptions to conclusions. So, though he proposed the natural deduction system, he considered it somewhat ugly, since it, for of course, one important reason for him was, if you look at reductio ad absurdum, they're doing something weird. I mean, if theoretically the rules for and or are not symmetric, they're not dual, and the proof rules are asymmetric. In a rule, you're allowed several premises, but only one conclusion, right? So, and you take the tree shape very literally. The idea of proof rules with many premises and one conclusion gives rise to a proof tree. And Jensen was even questioning that. Why shouldn't it be a graph, right? I mean, why should it be a proof net? This is what your modern positions call it. So, and an important thing for him was also the intuitionistic logic, which doesn't come up naturally in it. I must say it's not as ugly as it says, but in any case, Jensen was really after symmetry. So in the new system, every judgment called a sequent is symmetric, and the general form is that you have a sequence of assumptions and you have a sequence of conclusions. So this is the idea of a judgment, right? So think of these. So now from these premises, alpha 1 through alpha n, you derive a conclusion, beta 1 through beta n, and the way to read it, the interpretation is that the conjunction of all the formulas on the left-hand side implies the disjunction of all the formulas on the right-hand side. What you're saying is that if I assume that alpha 1 through alpha n hold, then I can derive beta 1, I can derive beta 2. So the disjunction of all of them is something like that. So this is the fundamental idea of a sequent. And the sequent calculus is to manipulate sequence. So how do you derive one sequence from another? That's it. So it's very close to natural deduction, but this very important distinction. And as you will see, it's almost a fanatical devotion to symmetry and duality. So the dualities of logic are baked into this. So the duality between true and false, between conjunction and disjunction, all these. So so you don't, like I said, a natural deduction, conjunction introduction and conjunction elimination are completely straightforward. If you take the dual thing, disjunction introduction is straightforward, but disjunction elimination is not. Right? To give you an example, there's a lot more arithmetic. And negation, for instance, is treated in a very strange way. So all that is something that gets into it. And as I said, he was the one. Now, for the theory of programming languages, there is a very strong computational interpretation of sequent calculus, which actually reveals hidden dualities in programming. And for instance, the input-output duality, reversing computations in one direction, production and consumption of resources, construction and deconstruction, structure and pattern. So usually when I teach a programming language theory course, I actually show the connection between these two, just like that, intuitionistic logic and these computational interpretations. But it's something important in essentially thing that is gone. Many years since I taught, and nobody's interested in these things anymore. But semantics of programming languages, there is very tight connection logic. So mainly because the sequent calculus formulates deductions that carry context around. So his main point is that the idea of having these sequences around is that these assumptions entail this conclusion in this context, in the context of some other assumption, other conclusions. Right? So you carry context around, and which is much like evaluation context of programs. If you look at functional programming, function programs, and the implementation, the most important thing is carrying context around, or configurations as using state transition systems. So, anyway, that is, yeah.
So, what is evaluation context of program?
Well, when you evaluate a program, or when you run a program, right, one is what is called a program counter, which keeps track of where you are in the program. So that's one. And in general, you have a context which tells you what are the values of the global variables, what are the stack, how many, which procedures you are running. So there is always an evaluation context in which you run. And at different contexts, the same program statement means very different. And that's
Right.
And so if you take the analogy between computation and deduction very seriously, these things actually pan out.
Oh,
So
okay.
yeah.
Yes, sir. Okay. Thank you.
So in sequent calculus, it's all about structure. The system consists of 3 classes of rules. And the so-called logical rules, which is the part that is similar to natural deduction. In natural deduction, where you had an introduction rule and an elimination rule, here you have a left rule and a right rule for each kind. Because you have sequence, there is a left-hand side and a right-hand side. So you have rules that say, I want to have this, so that in some sense, so these rules are all introduction rules in that sense, introducing on the left or introducing on the right. And then there are structural rules, which actually refer to the context or the sequence structure that you have in the rules. Remember that right in the beginning I was saying that a proof is a sequence of formulas. Right? But if you really think about it, the order matters only for saying that I derived this earlier. Right? Maybe. When I use the inference rule modus ponens, right, to derive beta, I should have derived alpha earlier. Alpha implies beta. But in terms of the logical content, right, it hardly matters. Right? So the notion of time that you have, the sequencing that you have, how serious is it? Now, there are logics in which, supposing you are allowed to assume P or not, right? Whether you assume P first or negation P first may matter because in the further conclusions that you draw. Right? Now, classical logic doesn't have this, but Gensen was interested in having a very general idea of a proof around where, like I said, the context may actually matter, the order may matter. So structural rules are to explicate the dependence if there is any. And then there are 2 core rules. So there are logical rules, structural rules, and core rules. There are only 2 of them. One is called the axiom rule, which is the axiom, and the other one is called cut. You'll see that. So what are these rules? So first we'll take up the logical rules because these are the familiar ones that we are dealing with. And so we'll assume that there are 2 propositional constants. Anyway, in natural deduction, I already introduced a propositional constant false, which is bottom side. But here we'll also use true, and as I said, for Gensen now, everything there has to be dual. I mean, you can't have one without the other. So duality is there. So you have 2 constants, true and false. And for true, there is a right rule. It says, well, gamma is any sequence of formulas you've got, delta is any sequence of formulas. So this rule says that no assumption is needed. On the right-hand side, you can always put a true. You can read it as anything implies true. Right? Whatever assumptions you make, I can always conclude true. And in any context. Right? False left rule, it says false implies anything. Right? Whatever context you have got, and whatever assumptions and conclusions, you can always throw in false on the left hand side. False as an assumption is okay because. So now you've got 2 constants in the language, 2 propositional constants. So you have to have right rule and left rule. First thing is there are no left rule for top or right rule for bottom. Basically true, putting it on the left hand side, well, true is too weak to imply anything, right? And false is too strong for anything to imply. You can't have alpha implies false. Right? So you have, and similarly, you can't have true implies anything except true. Right? But then true you can always put on the right side. So there are no rules for this. So these are not derivable. That's it. Okay? So this is the most basic rules. Then you have conjunction, and that's the easiest connector. It's exactly what we have in the natural deduction system. The right rule for conjunction is if you have derived alpha on the right hand side and beta on the right hand side, you can combine them to have alpha and beta. And that's also something. No, you can check the soundness of these things as we go along, right? What is this saying? The conjunction of all these things implies alpha or, and the same conjunction implies beta or this. Now, if a formula gamma implies alpha is valid and gamma implies beta is valid, then gamma implies alpha or beta is valid as well. I mean, alpha and beta is valid. Yeah. So you plug it in and check that this is actually true. So gamma implies alpha is valid, gamma implies beta is valid, and gamma implies alpha and beta in the presence of obvious distinction. So simplest way to make sure that you understand this is consider a model that makes the gamma true, and if it makes this disjunction false, it will make all of these disjuncts false. In particular, it will make alpha and beta false. If that model makes alpha and beta false, it must make one of those things false. Let's say it makes alpha false, but then you're going to get a contradiction. Right? Because you know all of delta is false. So if the model satisfies gamma and makes alpha true, it must make alpha true. So that's it. So yeah, so this is the right hand rule. And what about the left rule? It's exactly what you would expect. If you have assumed alpha, you can always assume alpha, and beta, nothing will go, because the delta depends only on alpha and gamma. So adding an extra assumption doesn't hurt you, so you can always. And you can add on the side, so you have two left. Now, so is the rule for conjunction clear? So it also gives you an idea of how the sequent calculus proceeds. You have right rules and left rules. Yeah, that's the main idea. And so on the right hand side, you have to strengthen things. That's important. Right? On the left hand side, it's assumptions, so you can weaken things. Assumptions can always be weakened, conclusions can always be strengthened. This is the slope. I hope this is clear. So now what about disjunction? Now, and this is the beauty of sequent calculus, you don't need to ask. It's exactly due. So you don't have the kind of asymmetry that we had in natural deduction. Well, for conjunction, you had two left rules and one right rule. So for disjunction, you have two right rules and one left rule. It has to be like that. And for whatever you did for conjunction to the right becomes the same thing for disjunction to the left. So here, for instance, you have, if you have assumed alpha and got something, if you have assumed beta and got something, it doesn't matter, throw in alpha or beta as the assumption. Right. In particular, consider the case where beta is not alpha. This is the case analysis that we were talking about in natural deduction. Assuming alpha, you get something. Assuming negation alpha, you got something. In all cases, that's a particular case. This is the general case. And here you are only weakening. Right? You've derived alpha. I mean, you've concluded alpha. Of course, you can always conclude alpha or beta. So this is the meaning of disjunction. And yeah. So is it clear? Any questions about this? Okay. And negation is simply beautiful. I mean, there reductio ad absurdum, there is nothing like getting a contradiction, all that is gone. There is a, what is the right rule? It says if you have assumed alpha and derived something, I can conclude negation alpha, or if assuming alpha I have derived delta, I can always derive either not alpha or delta. That's exactly what it says. And symmetrically, if you have concluded alpha, I can always make negation alpha as one of my assumptions, right? Because we have already said either alpha holds or delta holds, right? So in the case where negation alpha holds, delta must hold. That's the meaning of negation. So it simply moves left and right. That's all, like we did. So it's a strict symmetry, and that's very important. Is it clear? Again, check the soundness. Assume this is, gamma union alpha gives delta as a consequence. We want to show that not alpha or delta is a consequence of gamma. Yeah. How do you show that? Take any model, assume that it makes all of gamma true. Then we want to show that it either makes alpha false or delta. Right? Okay. Suppose the model makes alpha false, you have true. Otherwise, the model makes alpha true. It makes all of gamma true and alpha true. Therefore, it is delta. So these are all fairly natural things to think about. But beauty now is the symmetry that you can make use of, the structure and the rules. And what about implication? And this is where the use of context comes in. The right rule for implication is what we have talked about as one part of the reduction theorem. Right? The difficult part of the reduction theorem that we proved in the Hilbert calculus is the right rule here. That is, if gamma union alpha gives you beta, then gamma gives alpha implies beta. Of course, you are doing it in the presence of other disjuncts. But, yeah. Is the idea clear? Again, this is sound, right? I mean, this is in fact, as I said. And in terms of consequence, it's very easy to see. Right? But what about how do you bring alpha implies beta to the And the rule is a little more complicated. It says, assuming gamma, I have derived alpha. And in another context, assuming beta, I have got these. Then I can combine the contexts. Right? Note that these two proofs, see, unlike the earlier proofs, here it's the same gamma. For disjunction and conjunction, I must use the same context. Right? The same set of assumptions, I have derived alpha and beta. It's very important. You can't change the gamma. Whereas, and this is what natural reduction is telling you, as far as implication is concerned, if you're going to make implication part of your assumption, then you can also get things from different contexts as long as you carry the context around. This turns out to be extremely. Yeah. So, once again, to see the soundness, assume that these are, assume consequence here, consider a model that makes gamma prime true and alpha implies beta true. You want to show that it makes either delta true or prime true. Well, we know that the model makes alpha implies beta true. So in that model, either alpha doesn't hold or beta holds. Right? Suppose beta holds, this tells you, well, this model makes all of this true, therefore it makes gamma prime true, makes beta true, therefore it makes delta prime true. So we have to. If it doesn't make alpha, yeah, so this is the two cases, alpha. If it makes alpha true, it must make alpha true. And otherwise, yeah. So in this case, you notice that it satisfies all of gamma, so it must satisfy one of the disjunctions. So either it makes alpha true or delta. If it makes alpha true, we are happy. So it's a fairly simple. And so this allows us to do precisely the sort of things that we were talking about earlier in natural deduction, but the main difference is that, natural deduction, there is a scoping rule which nests assumptions, and that nesting is gone. So you can simply deal with sequences. Yeah. So, if you recall, I pointed out that in natural deduction, if you keep making assumptions, when you discharge them, you can only discharge the innermost, and then the next outer one, the next outer one. So, and that creates problems in proofs. Like I said, it's okay for, I think it works reasonably well for human beings, but if you want to in general talk about existence of proofs, concept proofs, it's not easy. And this provides a facility for combining. And at the point, this also shows you, I think it's very important to realize that there are lots and lots of proof principles around. Right? If you just start with the notion of semantic consequence, I mean, these are all here. All these rules preserve semantic consequence. So there is a choice, right? So what is true out there, there are many arguments. But if you want to use a finite computational deductive apparatus, you have to make certain design choices about what you have available on the house. And that's why I said the connection with programming language theory is very, very strong. The constructs that you use and how you reason, compose these constructs is very important. That's what Jensen had very nice insight. So these are the logical rules. For the propositional constants true and false, we had right and left rules as many as we could. Then for negation, conjunction, disjunction, implication, for all of them we have got right and left rules. So now we go to the structural rules. What are the structural rules? The first is weakening. It says that you can always weaken your assumptions and strengthen your conclusions. Right? If you have already derived delta from gamma, then you can always write alpha or delta. Right? No problem. This just says that comma on the right hand side behaves as disjunction. Right? Remember, there is no comma in the logic. The commas that are there in sequence. So this actually tells you that, because if you look at the right rule for disjunction, that will use alpha or beta. You have alpha above and alpha or beta. Whereas this says I can always add an element to the sequence. So this is the formal meaning of saying on the right hand side, whatever you've got behaves like disjunction. And this is the one that says that whatever you've got on the left hand side behaves like conjunction. Right? So I hope the meaning is clear. Then this is weakening. Next is contraction. And this is to do with the fact that even though we write sequences, we don't really mean sequences. Right? In the sense that alpha or alpha is the same as alpha, alpha and alpha is the same as alpha. In particular, when I'm writing assumptions, how many ever you can reuse assumptions as much as you like. You can use conclusions as much as you like. They are for free. Right? And so there is no context dependence to assumptions and conclusions and proofs. They mean the same everywhere. This is the idea. That and for Jensen, these are things not to be taken for granted. And as we will see, there are logics where you won't be. And one more, and that it says order doesn't matter, right? Even though we write sequences, so basically what we are saying is that these are really sets, right? They are sets because the order doesn't matter, repetition doesn't matter. So the main order dependence of applying the rules in a particular way, all that is gone. It's just sequence, and you write sequence from sequence using whatever order. So this is great freedom.
Sir? Oh.
Yeah.
No, okay, sir. I have a question in the left rule. It's all right.
Yeah. Is it okay?
Sir, my question is that this delta prime, they are also sequence of formulas.
Yeah. They're all sequences.
Yeah. So, sir, why not just write alpha comma beta, then beta comma alpha? Why do we have to add delta and delta prime?
No. What we are saying is that you can do the swap anywhere in the middle, is what it says, right? By putting delta and delta prime on both sides, I'm saying that you can do the swap anywhere within the sequence. Yeah.
Okay.
You can do the swap here on the right hand side. You can do the swap on the left hand side. Otherwise, it might be that you are allowed to swap only at the rightmost or only at the leftmost end. Yeah. And of course, you can have a choice of many possible rules. Right? You can always swap at one end and keep pushing all the way. Right? You can do that, but that will blow up your proof, and also it may create all kinds of complications.
Yes. Thank you, sir.
Yeah. So the structural rules assert that the sequence structure in proofs is irrelevant. We might as well use sets in as antecedents and consequences. By the way, I never mentioned the term that gamma on the left hand side is usually called antecedent, and delta on the right hand side is called consequent. Yeah. Okay. So in fact, Gensen called them sequence, but Kleene was the one who called a sequent because the German term is too close to this word sequence in English. So, sequent is for him. If you read Kleene's book, Introduction to Metamathematics, and Kleene actually says that is a complicated reason for you take this part from antecedent, this part from consequent. But Kleene is worth reading. I mean, it's for me, I would say one of the books that made a major impact on me was in KFR Library, finding that Introduction to Mathematics. Okay, so we are pretty much done with the description of the system. So we have looked at the logical rules, we have looked at the structural rules, and then I said there are two core rules. One is the axiom rule, and this is alpha from alpha. Of course, that's the axiom. And then you have the cut rule. What is that? This is the only really complicated rule of sequent calculus. And and it's something to see what it says. Okay, what does it say? If I have assumed alpha and proved something, and later I have established alpha, think of it as a lemma. Right? If you have established the lemma, you can use it and then prove something. Then you can get rid of the lemma in the proof. Right? You make a claim, settle the claim, you can get rid of that. That's what it says. So it lets us use intermediate propositions and lemmas without them appearing in the final conclusion. In one context, I have derived alpha. In another context, I have assumed alpha and proved something. Combine the contexts and your proof is okay. So it says it's valid to allow additional hypotheses and alternate consequences in both the premises that you've got here. When you eliminate this proposition alpha from the thing, as long as you gather together in the conclusion carefully. That's what it says. And this is very nice because in sequent calculus, like I said, you do things in different contexts and put them together. You have to make sure that you carry, as long as you carry the context down clearly, it's okay. So this alpha has simply disappeared from the conclusion. Right? And so these are intermediate statements. And again, in terms of soundness, you can see that this is true. Why? Well, consider a model that makes all of this true. We want to make either delta or delta prime is true. Well, if this model makes all of this true, that model either makes alpha true or it doesn't. Suppose it makes alpha true, since it makes all of gamma prime true and alpha true, it must make delta prime true. Therefore, it makes this disjunction. Okay. Well, suppose it doesn't make alpha true. Well, it made gamma true, therefore it must make alpha or delta. Well, we have already said that the model makes alpha false, therefore it must make delta true, therefore again it makes this. But that's verification. The intuition behind cut is really this idea that something like what you do in natural deduction, you make assumption, but it's not that you discharge them by doing implication and worrying about scope and so on. No. You make an assumption. That's some proof somewhere. There is another proof somewhere where you have actually established under certain assumptions, combined the assumptions and conclusions. And here you cut out alpha from these two proofs. Right? Combined. That's why it's called cut. And this is a very important rule in sequent calculus. And it's actually cut that lets you get rid of all the problematic ones. Remember, there is no reduction ad absurdum, none of these things, right? And I told you that Gensen was bothered by the fact that in natural deduction, negation appears in all these funny ways, right? And here it's extremely neat. So what happened? And that's, you see that when you actually do the proofs, cut is something that's very useful. But yeah. Yeah. So if you work in intuitionistic logic, for instance, in intuitionistic logic, you cannot assert alpha or not. The whole point of intuitionistic logic is that reductio ad absurdum is not allowed. Only in a particular form. And so you have to be very careful about that, when you can do it. As I said, in particular, and in intuitionistic logic, you cannot have contradictions. Right? So from contradiction, anything follows. But alpha or not alpha is not that. And this is something that happens. And especially for there are a lot of parts of mathematics where you assert the existence of objects by saying that suppose the object didn't exist, something would happen, a contradiction, therefore it must exist. And gated proofs of that kind. How do you show the existence of an object by not producing the object, but by getting a contradiction from the assumptions? Anyway. So sequent calculus is very, very neat, as you've seen. I hope you agree with me that it's a
Jam, can I ask a question?
Yeah, please. Yeah.
This is Shonko here.
Yeah.
So, so the cut rule in sequent calculus is linked with the rule of modus ponens and Hilbert systems. Both are talking about dropping of hypothesis.
Yeah, well, but there is no implication, as you can see.
Right, exactly. That's my question. I mean, these two are related in the sense that you are forgetting something in the conclusion, but modus ponens is expressed in terms of implication, and we have this implication, introduction, and elimination rules in sequent calculus anyway. I mean, the left rule and the right rule. So how are these to be seen as, reflections of each other?
Okay, so, of course, in the sense of completeness, right? Everything derivable in one is derivable in the other. Right? But the proofs look completely different. That's the important. In natural deduction system and the Hilbert system, after all, implication elimination is modus ponens, right? That's what you are also saying. Right? But how is implication introduced? Implication is introduced in natural deduction system by making an assumption alpha, deriving beta, and then discharging the assumption to write alpha implies beta. That's how you do the introduction. Right? Now, cut doesn't have any of that. The main point about discharging assumptions, as I said, by implication, is that you carried the context into your formula. That is why the nesting of contexts in natural deduction is a complicated process. None of that. In cut, you just have these, as I said, these different contexts, and here you do it entirely through conjunctions and disjunctions. That's the difference, right? Rather than variations.
Sir?
Yeah.
Yes, so I was just thinking like this cut rule, there is some similarity with the transitivity of consequence relations which we prove, like reflexivity, monotonicity, and transitivity.
Yeah.
So that each consequence.
Yeah, I mean that is the soundness of this rule. The soundness of this rule is basically from that. Yeah. But as I said, the semantic consequence relation has all kinds of properties. To get them into proofs in some particular, and remember, those are with infinite sets. Here you have only finite sets.
Yes.
The main point is that you are trying to capture something infinitary like the semantic consequence relation and its properties using something finite, right? Proofs of finite objects. And so we want a strong enough rule that captures one of it. And cut is one of those things that makes a choice which turns out to be very useful. And by the way, all I'm saying is also related to mechanization of proofs. Right? We are moving away from the way human beings do proofs to a completely structural way of doing proofs. And that also means about mechanizing these things. So this is all about goal-directed proof search. Each logical rules identify a connective in the goal below the line and breaks it down into simpler sub-goals above the line. This is very similar to natural deduction. And look at the special case of the cut. What does it say? Suppose, I mean, I have used the empty set. I should write empty sequence, but I hope. Because by now we know it's not sets. So, if from the empty assumptions you have derived alpha, and from alpha you get the empty conclusion, what does that mean? The conjunction of the empty set, think of as true, and the disjunction of the empty set you think of as false. So this is from true I get false. I mean, this is the contradiction. So the empty sequent, where you have nothing on the left-hand side and nothing on the right-hand side, you think of as a contradiction. So this is the main. So if there is a proposition that we know to be both true, this is what it means. Right? It's valid. And false, then a contradiction. So the cut is actually a way of, saying a contradiction as a cut. Cut signals in the particular case. And the general case, of course, is and this is very important because in sequent calculus, you combine proofs from many different parts, and in the process, you may introduce contradictions. And the idea is to discover them, eliminate them, it's part of it. And for proof, theorem provers, for systems that do proof search, these are very important. And then something, but I wanted to point this out for another reason. On the other hand, suppose you actually have the empty consequent. I can always do weakening. Remember, I can strengthen the conclusion and weaken the assumptions. So I can get this as well, right? So you can, from these two, from a contradiction, you can get the empty consequent, empty sequent. And conversely, from the empty sequent, you can always get a contradiction. So this is that sequent calculus is consistent exactly when there is no proof of the empty sequent. Right? So how do I prove that a sequent calculus is consistent? Well, I prove that there is no proof of the empty sequent. In the case of the Hilbert system, we talked about a set of formulas being consistent if you cannot derive a contradiction from that set of formulas in the Hilbert system. But how do I prove that a Hilbert system itself is consistent? Only by semantic arguments, right? By showing soundness. Because suppose system allows you to derive alpha as well as negation alpha, then alpha has to be a valid formula, negation alpha has to be a valid formula, and that's not possible. Right? So you show that the system under empty assumptions doesn't lead to a contradiction by appealing to models. Now, Gentzen was not interested in it. I mean, this is true proof theory. There are no models. Right? You're only talking about derivations. Right? So, and here's the notion of consistency. And as I said, Gentzen's entire project was to prove consistency. And he wanted to do it without resorting to models of the yeah. So his idea was that you write down some rules, you write down some axioms for numbers in the theory, and you should be able to show it's consistent without actually appealing to any semantic structures whatsoever. So in any sequent calculus, how do you show it's consistent? By showing that the empty sequent cannot. And in Gentzen's 1935 paper, so-called hop charts, it's great insight into consistency. This is the cut elimination theorem. So what is that? So now I want to show that the empty sequent is not derivative. Well, how could we possibly build a proof of the empty sequent from axioms? If you look at it, and this is where, notice that in sequent calculus, everything is using your rules, right? Entirely structural. Now look at the structural rules and the logical rules. All of them will include at least one proposition built from a connective on either side of the reduced sequence. So the logical and structural rules cannot give you the empty sequence. If you keep only using logical rules and structural rules, you can easily show that a proof which consists of only structural rules and logical rules could not derive the empty sequence. This is a routine proof by induction. What about the axiom rule? Well, the axiom rule just says that if you've got alpha on the left hand side, you can get alpha, right? So you can't get an empty. So using structural rules, logical rules, and the axiom rule, there's no hope of getting the empty sequence. So the only inference rules that might ever deduce an empty sequence and therefore lead to inconsistency is the cut. And by the way, if you start doing proofs, you will see it's very easy to do consistent stuff because when you start combining things from very different contexts, yes, and that's something that all our reasoning. So, and thus the proof of consistency is the same as the proof of the cut elimination theorem. What does the cut elimination theorem say? You give me any proof of a formula, there exists a cut-free proof. Once I prove, this is the cut elimination theorem. What does it say? Take any formula, if it has a proof at all, it has a cut-free. If I prove that, and this is paper where he says that's all it means. Now, for consistent, and then he doesn't do it for just the system element, this LK, it's called LK. He doesn't do it just for this calculus, he does it for that. He carries out this project for arithmetic, showing that the formula is arithmetic, right? The axioms in the root, there is a cut elimination theorem. And that's another very important observation to make here. Note that the cut rule is the only one that does not have the subformula property. That is, what do I mean by subformula property? If you look at any rule, if you look at a complicated formula that occurs below the line, right? Only the subformulas of the formula occur above it. Right? So to conclude alpha and beta, if you look at the premises on top, you will use only alpha, whatever gamma and delta. Only the things that occur in the sequence below, the only rule that doesn't have the subformula property is the cut. Because if you look at the thing below the line, there is no alpha at all. Alpha by magic appears on one side and nothing left. So there are two proofs where alpha. So alpha is a formula of arbitrary length. So for proof search, this is very important because if I'm using if your system has subformula property, in fact, many, this is something that Suresh and I have been doing as a cottage industry for many years now. For many of our things, proof bounds is using subformula property to show that I can do the proof search in formula. So, in general, subformula property is something sacred to hold on. And they exist. Of course, you take a proof and remove cuts, the proofs may blow up. And that does happen. You cut three proofs that can be quite huge. But if you're only, you only have a system without, so subformula property is also very important. So cut-free proofs are algorithmically precious. So for proof search. And the sequent calculus is of central importance in proof science. Importantly, we can identify many important fragments of classical logic. So, as I said, Gensen's interest, he devised this whole thing to prove consistency. But later on, as I said, this has become the main tool of proof theory, and that's because you can look at many different things. For instance, by dropping the contraction rule, you get the so-called affine logics. By dropping the weakening rule, you get so-called linear logics. And by dropping both, you get relevance logics. A whole lot of logics are there. And I'm just dropping names here, I know, but to show you that there's a lot of insight into this whole structure. And then surprisingly, very small changes in the proof system give rise to inclusions. For instance, if you restrict the consequence to be at most one, that is, it's one-sided sequence. On the left-hand side, you have all these, and on the right-hand side, you have one, and make all the natural changes that you will make, you get inclusions. So, for instance, the OR left rule becomes, well, you have alpha here and you have derived gamma. I mean, forget the delta. Right? And all the rules are completely straightforward. And then you can actually show that alpha or not alpha is no wrong. Can I take another few minutes and show you some examples? Okay, here is I want to show something completely straightforward. Alpha and beta and gamma implies beta. Right. This is something, of course, it's true. It's only to do with the commutativity of conjunction. So you should be using whatever structural rules, conjunction rules, and there is an implication. So implication. So how does the proof go? Unfortunately, I don't know how to animate these things, but drawing this proof tree was complicated enough. So this is what we want. You start from below. Right? Now, what is the connective here? The main connective is implication. And I want implication to the right. So the rule you must apply is implication to the right. I mean, in sequent calculus, it's exactly this kind of structure. So if I'm using the implication tool to the right, how did I get the implication? By pushing the assumption to the left and the conclusion to the right. So do that. So what I want is the sequence alpha and beta and gamma to the left and beta and alpha to the right. Well, I've got a conjunction to the right hand side. So what is the rule that I apply? The conjunction right rule. That says, from this assumption, if I've got a beta and if I've got a alpha separately, I can combine. So push it up. Now, how do I derive this? Well, I've got alpha and beta and gamma. Okay? So by left rule, it suffices to get only alpha and beta, and then by left rule 2, left rule 1 here, you can see here that beta has been weakened. Weaken the assumptions, single. So that's all. So either you start from, but the thing is, you can never do bottom up. You could start with the answer and then say, here I can strengthen, weaken the assumption to alpha and beta. Here I can weaken the assumption to alpha and beta, and then I can add a gamma to the left side, and from there, you can combine. But as I said, this is not how it goes. It's goal-directed research. You proceed the other way, and the rules pretty much take you to the axioms, decompose things into smaller and smaller subgoals. Here, the so-called law of excluded middle. And how does the proof of this is classical logic. So in fact, you can prove alpha. And how do you do that? Well, you start with this. Here, I have used the contraction rule. What is the contraction rule? I just make 2 copies. Right? And in the 2 copies, I have used the OR rule to the right. So this is weakening from alpha. I have moved to alpha OR. Yeah. And then I use exchange. Push these 2 here. And now, again, I use, this side. So I've started with not alpha, I came to alpha, not alpha, so I have got alpha, and then negation rule says I can push it to the left hand side, and that's nice. Again, it's clear that some ingenuity is needed, right? I mean, there's no hope of just staring at it. How did this first step happen? How did you come up with the fact that you are using contraction here? But this is only to point out that not only are the logical rules, the structural rules also come in here. And you have to use the structural rules. Because the logical rules are very specific. They apply only to the leftmost or the rightmost, and then to the left disjunct or the right disjunct, or the left conjunct or the right conjunct. Right? And therefore, to get whatever you want to do to that position, you have to use, for instance, exchange, and you've got only one formula, you need 2 formulas, all that kind of things. Another example, and this is to show how cuts are actually useful. Now, remember that in the Hilbert system, the non-trivial part of the deduction theorem was this way, trying to show that if gamma union alpha derives beta, then from gamma there is a proof of alpha implies beta. In fact, I did a proof by induction and introduced the axioms in the process. Now, I don't need that in sequent calculus because that's in fact the rule for implication. So, whereas the other direction is not trivial. If from gamma I have derived alpha implies beta, then gamma with the assumption alpha I can derive that. How do you do that? Well, this is what I need. What I do is I use the cut rule. Since I've got gamma alpha and beta delta, I put in an alpha implies beta to the right hand side here and alpha implies beta to the left hand side here and use the cut. Now, how do I, for instance, here you can see, how do I have an implication on the left hand side? Well, an implication on the left hand side means that I should have the beta on the left hand side and the alpha to the right. And well, just write down, and I see that the axiom rule will just be because from beta to beta. And, so what about here? Yeah, here I first weaken it, and I use weakening to get rid of this multiple alphas, and then I bring it down to the form, which is what we had. Right? We had this, and we want to show this. So this is some proof that you are given. On top of that proof, you are building. Okay. Let me repeat what I always say. Right? These kind of formal proofs, it doesn't matter whether it's a Hilbert system or natural reduction or sequent calculus. By watching some, and least of all, at least if I was doing it on the board, I would actually start with this and do it slowly. Fortunately, in slides, that luxury is not there, and I'm presenting a finished proof to you. And I know that there is no hope of understanding the finished proof by just looking at something. So the only real way is to work it through yourself. But these files will be with you on this, and I can give you many more examples. So the thing is that to actually get used to doing these proofs. So of course I will send you some exercises for doing some of the proofs, and we already had a bunch of examples for the Hilbert system. Natural reduction, I think I did just one. Reduction of the Sequent Calculus reduction 3. But for simple propositional formulas, if you try out, dirty your hands, see how all these rules play out. Yeah, that's it. Any questions?
Jam, one question.
Yeah, please. Yeah.
So this, Vikram here. So this cut seems to be like a witness, right? So there is a.
Yeah. Oh, we'll get to quantifiers and witnesses. But you mean witness more in the sense of
yeah, that there is a some
computation,
right? So
certificate.
It's a certificate that from these antecedents, and we can combine. So, I mean, is there an approach which says there is a that the witnesses are of a certain size and so on?
Fortunately, I mean, as I said, in the process of eliminating a cut, you always blow out. So, and you can prove that that's unavoidable. So, yeah. I mean, otherwise this would be, I mean, this is propositional logic, right? P and P question is floating around. I mean, not right, in this particular case, it's the NP co-NP question that's floating around. You're doing proof search, you're actually looking at precisely that question. And so there is no easy answer to that.
Okay. Yeah. Thank you.
Yeah, but as I said, I mean, remember this is 1935, right? So Gensen's insight into propositional proofs is something remarkable, really. And after what, all this time we are still struggling with propositional proofs, right? We have no clue. We don't know the status of P and NP. So, and of course, Gensen was interested not in just in propositional logic. He's interested in not in first order logic. So, yeah, I mean, sequent calculus is particularly interesting if, as I said, proof theory and you look at things like linear logics. As I said, what does it mean to drop these weakening rule or contraction rule, etc. etc. What does that mean, really? Like in the case of linear logic, formulas don't represent truth values. Like Girard says, alpha and beta are not truth values. They're not about true and false. It's about cake. Having two cakes is not the same as having one. You make identical copies of two. Alpha is not the same as having alpha. So that's why weakening is not allowed. Contraction. Weakening is not allowed. So from alpha, you can't derive alpha. So it's like making copies. So he calls it a resource conscious logic. So this is to point out that if you were to think of deduction as computation, these things matter like hell. Right? After all, you have to write down your formula somewhere, these things somewhere. So you don't take it for free. And Genzen brought very systematic ways of thinking. Okay, so and so we have to upgrade all these things to quantum calculus. First, we have to do the Hilbert system, and then what is the system?